Good. So last time we ended off talking about some ways of making alkyl halides. They're usually made in particular from alcohols. And we talked a little bit about the characteristic reactivity of alkyl halides. And this time we're going to cover, I have two main ideas to get across today. One is another characteristic reactivity of alkyl halides, which is they can be converted into what are called organometallic reagents. So they're going to be species with a carbon metal bond. And yes, those are a thing. And then I also want to at least touch on, at least get through enough information to get you guys started on the idea of redox in organic chemistry. It's something we'll hit upon again and again, I would say repeatedly throughout both this term and next term. But I just want to get the idea on your radar screens at least and give you at least some ideas about how you can tell whether a particular organic reaction is an oxidation or a reduction, or one possibility that we should always remember, whether it's neither oxidation nor reduction. That's certainly also possible. Not every reaction is a redox reaction. So if we can get through that much today, I'm pretty happy. I actually had some reef questions ready for a polling session, but in my previous class, section 504, that meets just before you guys, we didn't even get to them. So I'm expecting we won't today either, but certainly do register your attendance so that you can get credit for being here. Um, just real truth time here. I am aware that you guys had to spend money on the Reef app, and I'm not satisfied with myself with the number of Reef polling sessions, because I really wanted that to be worth having bought. It's something I kind of feel bad about. Whether that means that I'm using more class time to explain things or do examples, that might be all right, but something I'll have to think about. But I'll certainly try to get to the reef questions next time. I really want that to happen at least once a week. I think at least if it's that much, then it's worth your having bought it. Good. So I think that's all I really need to say by way of introduction. So what are organometallic reagents? And why are we talking about them here in a chapter on alkyl halides? Well, it's because alkyl halides are probably the most common precursor to any given organometallic reagent. And the significance is if you consider any given alkyl halide, I think you're aware of the nature of the carbon-halogen bond, whether it's fluorine, chlorine, bromine, or iodine. Probably we're going to be using mostly alkyl bromides and iodides in order to make organometallic reagents. Alkyl chlorides can often work also, but we understand that halogens are, by and large, more electronegative than carbon. I think we're all aware of that. So that means it's going to be sucking electron density away from the carbon and giving it a partial plus charge. That means that alkyl halides are by and large going to be electrophiles. We would expect them to suffer nucleophilic attack from some nucleophile. And by the way, welcome to chapter 11. That's what we're going to be talking about to a large extent in chapter 11, is the ability of alkyl halides to act as electrophiles, as Lewis acids, if you will. But if we can somehow, by some wizardry, convert this carbon-halogen bond to a carbon-metal bond, then what's going to happen? We understand also that metals are all going to be less electronegative than carbon. Metals love to give up electron density, right? The way you know that is they like to form cations if they can, right? +1, +2, whatever. And so when we actually have a bond between a carbon and a metal that even has some covalent character, on which more in a moment, then we would expect the metal would be dumping electron density onto the carbon. It's going to be doing the opposite of the halogen. So whatever, again, the wizardry is that goes on here, over the course of that process, we have reversed the characteristic reactivity that we started with. We started off with this organic compound being an electrophile, and now it's going to be a good nucleophile, or perhaps a good Bronsted-Lowry base. and that by virtue of the carbon atom now having more electron density around it, that the metal is pushing onto it. So by just one, let's say by just say by one reaction here, we can reverse the characteristic polarity of that bond. We can convert a compound that used to be a good electrophile into one that will be either a good nucleophile or a good Bronsted-Lowry base, or even both. And so that's important. And we're going to learn some ways that we can take advantage of that manipulation, of reversing the polarity of the species. We're going to learn about 2 or maybe 3 kinds of particular organometallic species. There are scads others besides these, but we'll learn about the major ones. And we'll learn around 2 things that you can do with such species today. One of which, just to warn you ahead of time, is going to be very boring and quite far from being something synthetically useful. It's actually the opposite of useful. If anything, it's destructive, and it's the sort of thing that I won't say we would never do in organic synthesis, but very rarely. So we're going to learn other things that we can do with organometallic reagents later on that are much more synthetically useful. We're just getting started today. But we'll also learn one type of reaction that can actually be very powerful. So we'll get to that today also. So why are species like this good nucleophiles? How can we know that? Well, again, with the metal, essentially whatever the metal is, we're going to look at 3 metals today. We're going to look at magnesium, lithium, and copper as being possibilities, and certainly other organometallic reagents exist, but those are the 3 we're going to focus on today. And you know, those I think are the 3 that are in the chapter that we put the most focus on. But if the metal is pushing electron density on the carbon, then it means that organometallic reagents are going to act as if they were a carbanion. That's the type of reactivity they're going to have. So we'll define carbanion using a structure. Carbanion is a species with 1 lone pair in carbon and a minus charge. 3 bonds, 1 lone pair, and a minus charge. So if you work it out, the formal charge here is going to be -1. And these species, the way we know these are such good nucleophiles, well, we've got a carbon atom with a lone pair. It's really wanting to donate that lone pair and form another bond, because carbon is not very electronegative. It's not real fond of having a minus charge. Are we doing Grignard reactions? Yes, that's why I said magnesium. That's going to be one of the metals we look at today. Oh, but do you mean Grignard reactions with carbonyls? No, not here. We're going to get to that next term. But we're going to learn about Grignard reagents for sure. Anyway, so that's how we know that those species are good nucleophiles, good Lewis bases. But the way we know these are good Bronsted-Lowry, not just good, these are superb Bronsted-Lowry bases, is by looking at the conjugate acid. So the conjugate acid of a carbanion is just a species with a carbon-hydrogen bond. And as you know, carbon-hydrogen bonds are in general not very acidic at all, quite the opposite. So a species like this, generally, depending on what else is attached, depending on the hybridization of carbon, is probably going to have a pKa round and about the mid-40s to 60 and up. So these are very, very poor acids, very weak acids. So that means that their conjugate bases are going to be very, very strong bases. And if they can find a proton off of something, they're going to grab that proton with all due haste. So that's how we know that organometallic reagents have that kind of reactivity. They behave as though they were carbanions, and carbanions are both very good nucleophiles and very strong Bronsted-Lowry bases. And so we're going to learn about those types of reactivities, again, in part today. We're not going to go the whole way. We're not going to learn about their otherwise very useful reactions with carbonyl compounds until next term when we discuss carbonyl compounds. The various carbonyl-containing functional groups have always, for decades, been a real cornerstone of any organic chemistry 2 class. So that we'll get to that next term. Good. So I think with that, I've given enough by way of an introduction that we can get into the types of organometallic reagents that we're going to learn about today. And again, the first 2 metals we're going to do are going to be magnesium. We're going to learn to make Grignard reagents, and lithium. We're going to learn how to make organolithium reagents. And I would say, by the way, I don't know the mechanisms of any of these, and I certainly wouldn't expect you to either. I don't think any of these have particularly well understood mechanisms. But we do understand the types of products that we get out at the end. So I would say if we're going to make, let's start with magnesium. If we're going to introduce magnesium into an organic compound, we need to start with some alkyl halide. I would think any halogen will do, the bigger, except fluorine. Chlorine, that usually you can make a Grignard out of an alkyl chloride also. Alkyl bromides and iodides are certainly fine. Those are no problem. And what we're going to do is react the alkyl halide with magnesium metal. And again, please note, this is elemental magnesium. This is the metal. This is not a magnesium ion or an ionic compound including magnesium. So we do treat it with magnesium metal, which is normally sold in what are called turnings. They're like little pieces. They kind of look like bits of magnesium that are not exactly foil. They're a little thicker than foil, but they're kind of crunched up into little pieces. And so if you ever get to use magnesium, you might have actually in a Gen Chem lab, then you know what that looks like. The solvent of choice is going to be some ether solvent. Diethyl ether is fine. THF is also fine. And again, please be sure you know the structures of these. The thing that I want to avoid that I run into all the time, especially in the second semester, but the first semester as well, is people confuse diethyl ether and ethanol because they're just memorizing it's a thing with an ET and they don't really bother to try understanding what's going on here. Please don't let yourself do that. Diethyl ether and ethanol are completely different critters. They both get used as solvents, but ethanol is what we call a protic solvent, and we've defined protic solvents before. Protic species are those that have either OH bonds or NH bonds, at least one of either an OH bond or an NH bond. So that includes water, that includes alcohols, certainly. That includes carboxylic acids, right? Those have an OH bond. What about primary and secondary amines? Those are also protic species. Diethyl ether is not protic, it's an aprotic solvent. And so it's completely different. These two things, even though they both have an ET in them, are completely different species. So please think about these things when you write them down. Don't just try to memorize letters and numbers. I promise it will not go well. Good, so as long as we aren't confusing those guys, we're in good shape. But any ether solvent will do. Diethyl ether is pretty common. Tetrahydrofuran is also pretty common. Remember a while back, we had run out of both. And so I used dimethoxyethane, that worked fine. Or did I use methyl tert-butyl ether? Either way, any ether solvent will be fine. And the result, again, the mechanism is not well understood, but the end result winds up in insertion of the magnesium atom into the carbon halogen bond. And again, I certainly don't know how that happens, and I don't believe anyone does. I don't think that's, to this day, something that we've really cracked. But I am being so bold as to draw a carbon magnesium bond here, and we'll do a few examples, don't worry. That brings up another thing that I should probably mention. You know, why am I daring to draw a carbon metal bond? I thought all bonds to metal were ionic bonds. And it's not that simple. I do want to take you back to your Gen Chem. If your class was anything like the Gen Chem classes I taught, depending on your book and on your professor, they discussed bond polarity and classifying bonds based on the electronegativity difference between the two atoms in question. And you had your table of Pauling electronegativity values, which I still don't expect you to memorize that. But you could use that in order to make that determination. And so they probably, if they did it the way we all did it when I was teaching Gen Chem, they probably told you to find the electronegativity difference between the two elements in question. And from, based on that number, you would compare it to other numbers you were given and the one you are probably given one number rounding about 0.5 or 0.6, again, depending on your book and on your professor. And if the electronegativity difference was less than that, then you probably classified the bond as nonpolar covalent. The extreme case, of course, being in something like H2 or Cl2, where the two atoms are the same and the electronegativity difference is 0. Doesn't get any more nonpolar than that. So that was one cutoff point. And then you probably had another one that was rounding about 2 or 2.1. And you said that if the electronegativity difference was greater than that, then you classified the bond as ionic. And anything in between you called polar covalent. At least that's the way I did it when I was teaching Gen Chem as well as organic. And as you can probably tell, as you probably even figured out at the time, those numbers are bogus. They're just a simplification that make it easier for a first pass through that material. But the numbers themselves are not important. What we really have in terms of bond polarity is a continuum between, at one extreme, again, where the two atoms are the same and the electronegativity difference is 0. That's a completely nonpolar covalent bond. And at the other extreme, you might consider a bond between, I don't know, cesium or rubidium, one of these low down there alkali metals, and fluorine. You know, you can't get a larger electronegativity difference than that. You're at somewhere between 2 and 2.5. And of course, those bonds are completely ionic. There's absolutely no sharing of electron density. Anything in between, we can talk about it. Anything in between is going to be somewhere along that continuum. But you can actually wind up with bonds to metal having some covalent character, at least in the case of it being bonded to a carbon. So there will be some degree of, some degree of covalent character there. Certainly a very polar bond, but some degree of covalent character. And that's why I am daring to write a bond between carbon and magnesium. The same is going to be true of lithium. The same is going to be true of copper. We find there to be some degree of covalent character in these bonds. So we can speak of carbon metal bonds. Good, so basically, if you take almost any alkyl halide, and it's pretty general for R, any sort of hydrocarbon group is fine. It can be primary, secondary, tertiary, aromatic, vinylic, these all work. You just don't want the group R to have any functional group that's going to react with a Grignard reagent. So nothing protic, no carbonyl groups along there. If there is some group that's in the group R that reacts with organometallic species, you're not going to be able to get the reaction to occur. But anything else, any hydrocarbon group for sure, anything any groups that are not protic or do not contain a carbonyl group, you're fine, and you can functionalize it with a magnesium atom like that, and you'll get a stable compound, and you'll be fine. As an example, let's take this compound. I'm just sort of making one up arbitrarily. If we were to treat that compound with magnesium metal, again in either diethyl ether or THF, hopefully you remember the structure of THF. It's a 5-membered cyclic ether, but you can use either diethyl ether or THF in most cases. I would expect that magnesium would insert in that carbon metal bond, and the same would happen if this were a chlorine or an iodine. I don't want you memorizing its BR. It's not necessarily BR, but here it is. But I would expect you would get that Grignard reagent in pretty good yield. If not that you could even buy a solution of that Grignard reagent. There's a lot of Grignard reagents that are commercially available. They're sold as solutions, usually in diethyl ether or THF. And they will tell you it's 1.0 molar of whatever Grignard reagent in that ether solvent. But if it's not a commercially available one, you can generally make them. So that's one organometallic reagent you need to know about. And again, I have no idea what that mechanism is. If you tell me, we'll both know, but I don't believe it's known. Actually, if you said you knew it, I'm not sure I would believe you, because my understanding is it hasn't been solved yet, though I know multiple people in chat who are going to try to prove me wrong. And that's fine. If I'm wrong, I'll be happy to admit it. What would be an example of an incorrect R group? Well, like I said, it's something protic. We defined protic. Protic means it has either at least one OH bond or at least one NH bond. Or if there's a carbonyl anywhere in it. That would be an incorrect R group. You would not be able to get a reaction. So you'll be shown particular examples of incorrect R groups in the OWL assignment. I'm trying to push you here. Okay, fine. Here's a compound that you could not make a Grignard reagent of. This one. Do you see how this has a carbonyl? So if you're given something like that, you'll just put down you can't get a Grignard reagent. Does that make sense? Does that, yeah, okay. So you'll just put down you can't get it. You would not get, well, the carbonyl would prevent the reaction from occurring to give anything clean or anything useful. So likewise, if it had an OH group anywhere in there or an NH bond anywhere in there, you can't get the Grignard reaction. Same is true of alkylithiums. And those we get by treating an alkyl halide with lithium metal. And you do need an excess. So you do need to put down either 2 lithiums, this is Li, or excess lithium. Either of those is fine to put down. And it would be best practice if that's what you were given in a problem. It should make it clear that you have an excess of lithium. You need at least 2 equivalents, and I'll show you why in just a moment. As for solvents, you just want it to be aprotic. You can use ether. You can also use an alkane. Quite often hexane or pentane is used as a solvent with these. So either an alkane or diethyl ether is a good choice. And you will get the carbon halogen bond replaced with a carbon lithium bond. Now the reason you need 2 equivalents of lithium is you will also get the lithium halide as an inorganic side product. The problem will make it clear if you have to put that down. OWL will sometimes ask for that. They may even want you to make a separate sketcher with Li plus in it. Let me just make sure that hand went up real quick. I want to make sure I didn't make a mistake. Good, yes. So let me just repeat that in case it clarifies that. So you need to know that you need an excess of lithium. You can put either 2 lithium or excess lithium, EXE period. Both are fine, yes. Li, let me write that again and make it clearer. There we go. So you get a carbon lithium bond. And well, let me do an example. Let's say we took, I don't know. I gave this example last time. So let's say that we took this aromatic iodide. Here we've got an ether functional group. This does not fall into the definition that we gave of protic. There's no OH bond. There's also no carbonyl. So that's how you know this is fine, and we will get the corresponding Grignard reagent, or sorry, alkyl lithium. Let's say we treated this with an excess of lithium, at least 2 equivalents. Let's say we used pentane solvent or hexane or diethyl ether, doesn't really matter, but I would expect that the major organic product would be replacing the carbon iodine bond with a carbon lithium bond, and everything else would stay the same. This is Li over here. Let me do that again since I'm having trouble being neat. There we go. So that's what I would expect you would get. So we'll get to some examples of what you can do with these. Again, we're going to do one extremely boring example and then one somewhat more useful example. The other thing that I expect you all to know about alkyl lithiums and Grignard reagents is, for our purposes, they are interchangeable. They have the same reactivity. And I'm even hard pressed in any kind of practical sense to come up with an example where it matters which of those 2 you use. They have essentially identical reactivity. So that's another thing that you need to know. Grignard reagents and alkyl lithiums have, for all purposes, the same reactivity. And we're going to learn what that is. A lot of what that reactivity is we're going to learn next term when we talk about Grignard reagents. Oh, I forgot to say. So this is known as a Grignard reagent, Grignard, Grignard reagent. And these are called organolithiums. Oh, organolithium. Spelled like that. And the definitions are as shown. We're defining those two words with structures. But any compound of this type is known as a Grignard reagent. Any compound of that type is known as an organolithium. I think Grignard is a French name, so I'm probably mispronouncing it since the language I learned in school was German. So I don't know, Grignard, something like that. But anyway, that's how that's spelled. Good, and we'll learn in just a second what you have to know about what these things do, one step at a time. But I just want to make sure that everyone is clear on what these reagents are, and these are examples of them. Everyone okay so far? All right, well, everyone seems to be fine. Okay, so what can you do with these? Well, quite a lot, actually, most of which, as I said, we'll learn next semester. But again, alkyl lithiums and Grignard reagents are interchangeable. It really does not matter which one you use. In real life, we would make the decision based on which is easier to make, or better yet, which is easier to get to buy commercially. But generally, that's what we would do in real life. But for our purposes, they are interchangeable. Whatever one will do, the other will do. Good. So one of the things that these reagents will do is react with protic species. We said that before. And again, we've defined what protic species are. A protic species or a protic solvent is something that has either at least one OH bond or at least one NH bond. Those are what we call protic species. And we gave examples of what those are. So both of these types of compounds will react with a protic species, water, alcohols, carboxylic acids, etc. And that mechanism is very clear. That mechanism we know already. So maybe I'll use these particular organometallic reagents as an example. Let's say that we took this particular Grignard reagent and we added water or a carboxylic acid or maybe an alcohol like ethanol. CH3CH2OH. Well, you will get an acid-base reaction, and that mechanism is very clear. That one we certainly know. But what will happen is the electrons in the carbon-metal bond will swing away from the metal, remain attached to the carbon, and pick up the proton from the protic solvent. So it's just an acid-base reaction. We've done reactions like that quite a lot so far. So you just wind up protonating the carbon, and in the end, your major organic product will look like this. So there'll just be an extra CH bond here, which you can draw if you want to, but if you don't and you use line angle drawings, then it's understood. So something like that would be fine. That would be the major organic product. Al will let you know if you need to put down anything else besides. All of your other compounds, all of your other products are going to be inorganic. I guess you'd get like magnesium methoxide or something like that, as well as magnesium bromide. So the question will tell you if you need to put anything else, but the major organic product would just be this hydrocarbon. And again, that's why I say this reaction is, oh, it doesn't say when you, again, the name sounds French to me, but I don't know. I just am not strong enough in my history to know. But again, the major organic product will be this hydrocarbon. Okay, let me clarify this arrow. What this arrow means is that the electrons in the bond are remaining attached to this carbon, and they swing away from the metal. That makes sense. Metals want to give up electrons. They remain attached to the carbon, and they pick up the proton. This arrow, we've seen ones like that a bunch of times. You're just breaking the hydrogen-oxygen bond. So that's what this arrow means. And it doesn't have to look exactly like that to be right, but you want to show it's starting and ending in the right place. And what I'm trying to show here is that it remains attached to the carbon. So that's the main thing that you need to know. This arrow shows the electrons remaining attached to the carbon and breaking away from the metal, which is more than happy to give up the electrons. Since they remain attached to the carbon, they're forming a new bond between carbon and hydrogen. And then we'll, of course, deprotonate the protic species, whichever it is that we're given, and you will get the hydrocarbon. So this is really an almost counterproductive reaction. You know, we put all this trouble into getting this nice carbon metal bond in there, and we're going to waste it by replacing it with a carbon hydrogen bond, which is boring. So that's the way I tend to think about this, and I want to kind of pass that on to you too. So we normally don't do reactions of that type. It really is destructive or counterproductive. But that is one reaction that we're going to learn so far. That mechanism we do know. The mechanism for forming the organometallic reagent, not so much. But that mechanism we do know. We could have done the same thing with this alkylithium reagent. We could have treated that with any protic species. So that ether group is along for the ride. And if we treated this with, let's say, I don't know, butylamine, BuNH2, Bu for butyl group. Well, but the mechanism is going to be the exact same idea. Here's my butylamine. And so the electrons in the carbon-lithium bond are going to swing away from the metal and go towards this hydrogen. It's going to take off H+, and we're going to form a new bond between carbon and hydrogen. This is not the only correct way to draw that arrow. And again, you can look at the little addendum to the chapter 6 class notes to give you some other ideas of correct ways of drawing it if this doesn't work for your learning style. But again, we'll break the hydrogen-nitrogen bond. I could have gone for the other proton also. And in the end, we'll just get ethyl phenyl ether. I'm sorry, I'm going to have to put it up here just because I ran out of room, but it's the same thing, of course. So, so you'll replace the carbon-lithium bond in this case with a carbon-hydrogen bond. You can write the CH bond in the hydrogen if you want to. You can. But as long as you're using line angle drawings, it's understood, and you don't have to draw it if you don't want to. Good, so that's pretty much one of the two reactions we're going to learn about in terms of both Grignard and alkylithium reagents, but they are interchangeable. There's no significant difference in how they react. Good. And I promise you we'll learn some much more interesting things to do with both reagents next term, but we will always find that the two types of reagents, organolithiums and Grignard reagents, are interchangeable. It does not matter which you use. And if I were making a decision, it would be based on what's easiest to get a hold of. So these again are the major organic products. The question will make it clear if you have to show the inorganic products, but basically you would just get the anion of either, you would get whatever is left after taking off H+. You would get the butyl group in NH- and then lithium plus. Or over here, you would get some mixture of magnesium bromide and magnesium ethoxide. So like I said, normally we don't show those. I've put up an old exam so you can see what typical question formats are for me. And Al will make it clear if you need to show anything else. They are weird. Sometimes they will literally want you to draw an extra sketcher, to make an extra sketcher box and put in Li plus or Mg2 plus. I don't know why. So read the directions for what you'll need to put. But we're mostly concerned with the major organic product. Good, so much for that. Any questions on just protonation of organometallic species? Which again, I can hardly think of a time when you would want to do that in real life. Good, let's see. I think that's all I need to say about that. Let's then move on to something a little more interesting that you can do with either organolithiums or Grignard reagents. Both of them will work. And that is to convert them into an intriguing kind of organocopper reagent, which is, these are called cuprates or Gilman reagents. And we'll write all that down in due time. So we're going to suppose that we start with some alkyl lithium. I'm going to write R1 lithium. And let's say that we made that by the usual method, starting from R1 halide, or we're given the alkyl lithium. Either will work. it turns out that alkyl lithiums react in a 2-to-1 ratio with, of all things, copper 1 iodide, CuI. And in the end, you get a really interesting looking species that looks like this. So you can think of, to the question in chat, yes, the answer is yes, yep. In any case, where was I? So you can think of this as having 2 R1 groups attached to the copper. It's a species of this type. And that's the reason that you need 2 alkyl lithiums. I think you'll also get lithium iodide out of this. So you can write this either way. This is what this means. But I don't care which way you draw it, but if you're given something like that, I expect you to understand it. And so, ooh, what's all that then? And so I think you would also get lithium iodide as an inorganic side product. But this intriguing organic copper species, that's what's known as an organocuberate, or even just cuberate, or a Gilman reagent, Gilman. I think it's just one L. And again, I don't really care if you know what they're called. Mr. Gilman might, but I'm much less concerned about that than that you understand what these things do. And they can do they have pretty interesting reactivity. Once you have this Gilman reagent, and again, you'll always know what you have. You'll have either done the reaction yourself just then, or you'll be given it. I should also quickly mention, I have no idea what that mechanism is, and I really don't believe anyone does. There's probably a few people who think they do, but I don't think I believe them. Good. And yes, I will make so bold as to say that. Now, these Gilman reagents, in turn, and we'll do examples. Don't worry, we will do examples. We'll do at least one. Gilman reagents of this type will react with any kind of alkyl halide. Again, I don't know that I'd use a fluoride. Certainly bromides and iodides are fine. Chlorides will probably work also. And what you get out of it is, in terms of the major organic product, you just get the 2 alkyl groups connected. And we'll do an example, don't worry. But what you need to know is, in order to figure out what the product is, and again, we don't know what the mechanism is, what you need to know is you first need to look at the cuprate and find the alkyl group that's attached to copper, whatever it might be. It might be something you've never seen before. But figure out what that alkyl group is. That's the first step. The second step is you look at your alkyl halide and figure out what that alkyl group is that's attached to the halogen. Could be bromine, could be iodine, could be chlorine. And the third step is you just take those 2 alkyl groups and attach them together. Just make a new carbon-carbon bond. And that's going to be the major organic product. Now, it's not going to be the only product. There are going to be some inorganic side products as well, one of which I would expect would be the lithium halide, lithium iodide, bromide, or chloride. And you will also unfortunately get, let me do that again. You will also unfortunately get, let me do this right now, R1 copper. This species here that has just 1 alkyl group attached to the copper. Before the reaction, we'd actually gone up from copper 1 to copper 3. So the copper had been oxidized and inserting into that. But we go back down to copper 1, and you get this kind of species, which is usually just called an alkyl copper or an organocopper. And unfortunately, that guy is dead. I'll even put a frowny face. It's dead. Those things don't react with anything. And so that's one drawback of this reaction, is you lose one of these alkyl groups. We had to take 2 equivalents of our alkyl lithium to react with copper iodide in order to make the organocuberate. But yeah, waste 1 to use 1. I like that, yes. So once you have that organocuberate, unfortunately, you're only going to be able to use 1 of those alkyl groups. The other one goes to an alkyl copper and is useless. So that's one drawback of this reaction. Are there ways around that? Yes, there's people who have replaced the other alkyl group with something else and it works just fine. But I don't think we need to go that far here. So that's the shortcoming of this reaction. But there is also one thing that's very positive about this reaction, which is we formed another carbon-carbon bond. We formed a new carbon-carbon bond in exactly the place we wanted to, in a way that we can predict. We just need to look at this alkyl group and look at that alkyl group, and we'll do an example, don't worry. But we just need to look there and connect the two together, and that's where the new carbon-carbon bond is. And one thing that I think you ought to know is anytime we can form a new carbon-carbon bond in a controlled fashion, that's money in the bank in terms of, that's I can't hear you over the sound of all my money. That's what's going on there. Because anytime you can form a new carbon-carbon bond selectively, that's big. That's forming a larger and more complicated compound from a smaller one. And this is exactly what you need to do if you're in the pharmaceuticals industry, for instance. That's how and you may not do it this way. There's other reactions that form carbon-carbon bonds too. And also they can't hear you over the sound of all their money. So same thing. But the more possibilities we have for forming carbon-carbon bonds, that's big. That's really practically useful in anything that has to do with organic synthesis. Pharmaceuticals is just one example, but there are many other industries as well that have to do with that. So let's look at an example of this. Let's say that we had, oh, let's go crazy. Let's say that we had this organolithium. Either we're given it or we made it by starting with the corresponding alkyl halide. We'll take two of these and we'll react it with copper 1 iodide. And I would expect that we would get two of these attached to copper and also a lithium. Let me write that again and make it neater. And some students say they have trouble understanding what's going on here. So you can also draw it like this. You can just put two of those alkyl groups onto the copper. But if you find the parentheses confusing, then you can just draw the R group out twice, something like that. I don't care which way you do it. They mean the same thing. I was going to say to me, but they mean the same thing, period. If I didn't exist, they would mean the same thing. So you can draw the cuprate either way, whichever way is better for your learning style. I don't care which way you put it down. And now once we have that, well, let's treat this with some other organic halide. What about iodobenzene? Oh, actually, let's use colors. Yeah, let's use colors. And probably all this is going to be done in diethyl ether, by the way. So you can put Et2O the whole way. Again, the problem will make all that clear, at least I would hope. But what we'll do is we'll connect this alkyl group. Actually, let me do that again. I'm running out of room, so let me do it this way. Since I'm running out of room. I would expect that you would get, so you see I've drawn the group that's attached to the copper, and I'll attach to that the other thing that's attached to the halogen. And that's it, you're done. Mechanism is completely unknown, to the best of my knowledge anyway. So that's what you do. You look at what's attached to the copper and what's attached to the halogen. It can be chlorine, bromine, or iodine, and just connect them. Make a new carbon-carbon bond. And that's basically it. So, so that's a very powerful reaction. We can form new carbon-carbon bonds. Got like 3 minutes, and I still did want to say something about redox in organic chemistry, at least enough to get you guys started. But before that, any other questions on Gilman reagents and what you can do with them? Nope. Well, that's one nope. There could be, what, 140 not nopes, but that's fine. Good. So let's just say I've just got a few minutes, as I said, but let me at least get you started on organic redox. And I would say the only surefire way to know whether reduction or oxidation or neither of the above is occurring in an organic compound during a reaction, the only surefire way is to find oxidation numbers of carbon. And that can be a little bit tricky, because carbon can take on any integral oxidation number or any integer oxidation number between -4 and +4. So all of those integral values are allowed. The only the only one that's worse than carbon is nitrogen, because nitrogen can be anything between +5 and -3 and +5, including several fractions. So nitrogen's dreadful. At least carbon oxidation numbers are only integral. But one principle that some of my students and I kind of jointly discovered in class one day, and I've put this in the class notes, so you don't need to worry about writing this down. It's already in the chapter 10 class notes. One thing we discovered was that hydrocarbon carbons, so carbons that are only bonded directly to hydrogens or other carbons, their oxidation number is minus the number of hydrogens directly attached. And as I said, that's in the class notes, plus you can rewind the YouTube video and watch me say that several times if you like. So just to give an example of a reaction that we actually know pretty well, let's contemplate whether halogenation of methane, which we know you can initiate with heat or light of the right wavelength to give chloromethane and HCl. Let's figure out whether that's oxidation or reduction or neither. Well, this carbon is a hydrocarbon carbon. It's bonded only to hydrogens, and there's actually not even any other carbons. You know from Gen Chem that hydrogen is almost always +1. The only time it's -1 is when it's in a hydride salt with a metal, or maybe something like borane. But certainly when carbon's involved, that's going to be normal +1 hydrogen. And so the carbon has to have the oxidation number of -4 in order to add up to 0, right? You want it to be a neutral compound. So I will say, in order to understand what you need to know about this, you need to understand about oxidation numbers. So you might need to review that from Gen Chem. Well, what about over here? Again, we want to make sure that we wind up with a neutral compound. So each of the hydrogens is still going to be +1. That's normal +1 hydrogen. Likewise, oxygen is almost always -2 in compounds. Of course, except for O2, right? The element has oxygen with an oxidation number of 0. But when oxygen's combined with something else, the oxidation number is almost always -2. The only time it's not is if you have a peroxide, which I think you would notice. So likewise, hydrogen's almost always +1. Halogens, generally going to be -1, especially in organic compounds. These are normal halogens with one bond. So if we add all that up, we have 3 times +1 is +3, -1 is +2. That means our carbon has to have an oxidation number of -2. And so if you compare, we've gone from -4 to -2. The oxidation number is going up. So that's going to be, this reaction would be an example of an oxidation reaction. And you could say the process of halogenating the alkane is going to be an oxidation reaction. And there are other ways that you can determine this too. We'll have more to say about redox in later chapters too, I think in chapter 9. One of the things we'll discover is if you have more bonds to hydrogen in the starting material than in the product, then that's also an oxidation. Or you can flip that on its head. And we'll say all this again in chapter 9. It will all be in the class notes. You don't need to worry. I just want to get you guys started thinking about the idea of redox. And I'll end with this. One other thing you could say is that the product has more bonds to an electronegative atom, like a halogen or oxygen, than the starting material does. And that's another sign of an oxidation. So I just wanted to get you guys started on thinking about redox and organic chemistry. I'm sure we'll have more to say in chapter 9. Good, well, I'm out of time, so I will see you all on Friday.